All right, welcome back. Today we are going to discuss section 10.3, ellipses with a center point at 0, 0. As you know, we kind of go out of order in this chapter, so we did 10.1 and 10.2, and then we did 10.5. Now we're going to go back to 10.3, which is an ellipse. That's an oval-looking shape. So we're going to look at the standard and general forms of those equations as well as how to graph them. So a couple background terms here before we get rolling. So this is a very basic ellipse. It's a set of all points whose distance from two fixed points, called foci, have a constant sum. So you'll see these points here. These are called the foci. And what they're talking about, that constant sum, let me just show you the next slide real quick. If I were to add this distance, if I picked any point on this ellipse, for example right here, if I were to take this length plus this one, so D1 plus D2, it would equal the sum of D3 plus D4. Or if I pick this point over here and I drew a segment from this foci to this point and from this one to here, those two numbers would add up to the same as these two or the same as these two. So the distance from the foci always adds up to the same thing. So that's where you get that definition of the constant sum. The focal axis, that is the main axis through the center point and the foci. So if you think of a surfboard, this is the long way. So this surfboard, like if you're carrying it underneath your arm, the focal axis would be this way. If you stuck it up in the sand, then it would run up and down, and that would be the focal axis. The center point, that's halfway between the foci. There are four vertices. You have two on the focal axis, otherwise known as the major axes, and then you have two on the minor axes, and that's the chord through the center is perpendicular to the focal axis. So the focal axis is the same as the major axis, and then the minor axis is obviously the other one that's perpendicular to that. So four vertices as part of a ellipse. Okay, so you'll notice this equation is very similar to a circle where we have x squared plus y squared, and a circle is always equal to r squared. And then if you have the same coefficients here, so there's always over 1. With an ellipse, these numbers can be different. And you'll also notice that x squared can be first or y squared, and that's going to depend on the focal axis, whether that ellipse is run horizontal or vertical. So if x squared is first, we have a major or focal axis of the x-axis. So this is horizontal, so think of carrying the surfboard under your arm. If y squared is first, that's like the surfboard being stuck straight up and down in the sand. So our foci is c units away from our center point, which is always at 0, 0 in this case. When we get to day 2, we'll move it to hk, but for today it's going to be at 0, 0. So c units left and right. If we're dealing with y, then it's going to be c units up and down. And then our vertices are just the square root of these numbers here, a and b, in both directions. So when you see the plus or minus, it's really a0 and negative a0, 0b, 0, negative b. Over here, 0a, 0, negative a, b0, negative b0. Then our major axes or semi-major axis, that's the x-axis, which means the minor axis, also referred to as a semi-minor, is the y-axis. And just the opposite over here. When you refer to semi or minor or semi-major, that's just half of it, but typically we just use the terms major and minor. All right, the Pythagorean relationship here, normally a squared plus b squared equals c squared. When we're dealing with an ellipse, a squared minus b squared will equal c squared. So when we have a and b, that allows us to solve for c. So for an ellipse, a squared minus b squared. Eccentricity, that's a measure of how round an ellipse is, and I'll show you that in the next slide. To do that calculation, we do c divided by a. So eccentricity, we use variable c for that, but c divided by a. And what does that define? The closer your eccentricity is to 1, the flatter, more narrow this ellipse becomes. The closer you are to 0, the more round, closer to a circle that the ellipse becomes. All right, so that gives us the background here, and we'll go through a couple examples and get you rolling. So for number 6, and I know you already have the picture here, but we'll talk about where we got that from. So again, how do I know by looking at this that this is an ellipse just from the equation and not a circle? because these two numbers are different. So if these two numbers were the same, then we'd have an issue and we'd have to get after how to change that and be a circle. But because they're different, and also because of this plus sign here, so because it's addition and these numbers are different, we know this is an ellipse. This is going to be our a squared. This is going to be our b squared. So we know a is 5 and b is 3. Since x is listed first, we have a major axis going horizontally. So we know center point 0, 0, and we go 5 units to the right and to the left. And then our minor vertices are 3 up and 3 down. So again, we got our center point at 0, 0. You got our vertices there. You see a 5, 0, negative 5, 0, 0, 3, 0, negative 3. And now I'll talk about how we got these foci points. So again, with an ellipse, they didn't tell us what C is, but we have A and B. So we know C is A squared minus B squared. So 25 minus 9 is 16. Square root of that is 4. So our foci is 4 units to the right and left from the center point. How do we know they're right and left? Again, because the foci are on the major axes. So that's how we got, by finding A and B, that allows me to get C. And once we have A, B, and C, we can find the foci and the 4 vertices. Again, for today, day 1, center point is always at 0, 0. When you graph this, just do the best you can through the verse. I don't expect it to be perfect. Kind of like when we draw our graph circles, rough sketches, do the best you can with that. Just make sure it doesn't look like a diamond. Try to round it off as best you can. All right, so now we have one that's not quite in the right form yet. So you see we have 4x squared plus 9y squared equals 36. If this was a circle, both of these numbers would either be 4 or both of them would be 9, so that when we divided, we get x squared plus y squared. Since they're not, we're going to divide by 36, and you'll see what happens here momentarily. So we're going to find the vertice and foci of this ellipse, and then we're going to sketch a graph. We'll do that on the next slide. So I'm going to divide here by 36. The reason I'm going to do that, I want this to equal 1. And so 9 over 36, it's really 1 over 4. 4 over 36, 1 over 9. A is always the largest number. So if this one happened to be 9 and this one happened to be 4, then you got to switch the order and put y squared first. So make sure when you do this division, you always put the bigger of these whatever number here is bigger, that's one goes first. So again, x squared is first. So major axes horizontally, minor axes up and down. If this was y squared first, then this parabola would go vertically like so. All right, this is a squared, so a is 3. This is b squared, so b is 2. Again, I can plug this in and find c. So 9 minus 4 is square root of 5, so 2.24 for c. From a graphing standpoint, again, center point, 0, 0. My vertices here, 3, 0, negative 3, 0. So 3 to the right, 3 to the left. And 0, 2, 0, negative 2. So up 2, down 2. The foci you can write as a decimal, or you can put the square root here, that's fine. 2.24, so we know it's a little bit more than 2 to the right and a little less than 2 to the left. Just kind of, when you get a decimal, fit it in there as best you can. So you can see my points are a little closer to 2 than they are to 3, and that's fine. And then again, we draw our ellipse as best you can. All right, last slide for today. You're going to see equations or basically examples like this where they're going to give you a sentence. They're going to give you enough details so that you can write the equation. So we got the answer here, but how did we get there? So it says we have an equation of an ellipse with foci at 0, negative 3, and 0, positive 3. So if you're just thinking about your foci, 0, 3, 0, negative 3, you've got them, they're up above each other like this. So we've got an ellipse that is going to go vertical. Since that's the case, y squared is going to come first. So if you're wondering why I did that, this one is running vertically based off the foci. Y squared goes first, then x. A is always the first one, B is always the second one, regardless of what x and y are doing up here. So from the center point to the foci is 3, so we know 3 is equal to c. And we know the minor axis has a length of 4. by telling us that the minor axis has a length of 4, so half of that, that's your b value. So half of the minor axis is b, so if the whole thing is 4, half of that is 2, so b squared is 4. Now that we have c and b, we can solve for a, so we know that c squared equals a squared minus b squared, and if we solve that, a squared is 13, so now I know 13 goes here, b squared is 4, that goes there. Just to go back to this minor and major axes, so b is always half the length of the minor axes, and a is always half the length of the major axes. So if they told you the major axis was 12, then a would be 6. If they told you the major axis was 21, then a would be 10 and a half. Typically, we try to stay away from decimals on that, but that can happen. All right, the second example here, find equation of ellipse whose axis endpoints are 6, 0, negative 6, 0, and 0, 4, 0, negative 4. So what they've indirectly told me here is they've given me a and b. And since they're only looking for the equation, we don't care about the foci, we don't care about any of that other stuff. We know the center is at 0, 0. So we went 6 units to the right and left. So a is 6, and we went 4 units up and down. So b is 4. So now if I square those, I've got a squared, b squared. The major axis is going horizontal, so that's why x squared is first. So x squared over a squared, y squared over b squared, equal to 1. And again, ellipses always equal to 1. So that'll sum up today's notes for day 1. Day 2, we'll get into what happens when the vertex isn't at 0, 0, and we start moving these things left, right, up, and down. All right, thanks a lot.